Good afternoon, friends. Today I am going to tell you buckling analysis of cold form steel columns using ABAQUS software. So, first of all, start ABAQUS. This will take a time. So, here this is the section with 900 length. So, we have to mention here the coordinates. Here will be 80, 0, here 0, 0, here 0, 200, here 80, 200. So either if you take the midline of this section and thickness is 2 mm, take midline of this section or take outer distance. Taking midline of this section is or center line of this section is better. So I will take a outer part. So we have to first take part, take part, click on part, then part manager, create. Since our cold form steel column or the they are made up of thin sheets, so we take them as shell and extrusion continue. Here dismiss. So we will take line command and enter coordinates here. First is 80 comma 0, enter 0 comma 0, enter then 0 comma 200, enter then 80 comma 200, enter, then press escape, then done. Then here we will have to select depth, that is 900 in Z direction. Okay, so this is our cold form steel member. Then go to property. In property we have to go to material properties, mechanical elastic. So here Young's modulus 2 into 10 to the power 5 and Poisson's ratio is 0.3. So after this, go to plasticity and plastic properties. Yield stress, suppose yield stress of cold form steel is 250 Newton per mm square. All the units must be in same same form or same SI unit. That I have taken here Newton and mm. So next step is section manager create. Suppose I give a name as buckle. So buckling of shell homogeneous, that is that is the member properties is same. Continue. Thickness, shell thickness you have to give 2 is a shell thickness. Here 2 is shell thickness. Then click on OK, dismiss. Then click on section assignment manager, click create. So here we will say select regions to be assigned for this section. So select this region and click on done and OK and dismiss. And then assembly. In assembly we have to assemble the parts. Here there are no parts dependent. Click on OK. Then go to step. In step click on create step. Linear perturbation. Then buckle. Then continue. Number of eigenvalues requested is 6. Suppose 6. So we will get vectors per use. Vectors is per iteration, that will be double. 6 into 2 equals to 12. And maximum number of iteration we have to take more number, that is 200 or 250 or 300 as per your requirement. Then click on interaction and then we have to create a reference point. I have CG at 18.528 mm. This x of CG is found out by 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 taking this as datum point, this, and you know how to find x of CG. A1 into x1 plus a2 into x2 divided by a1 plus a2, that is a is area and x1 x1 is this, for this x1 will be 1 mm for this, and for here x1 x2 will be 2 of this 200 mm flange, 2 mm plus here will be 78, 78 divided by 2, 2 plus 78 divided by 2, how much it will be 39. So we will have x of cg for web will be 39 and x of cg for flange will be 1, means area of flange into x of flange plus area of web into x of web divided by area of flange plus area of web, that will give you x of cg, that will come as 18.528 mm. So create reference point at x of cg. So x is 18.528 comma y will be 100 comma z will be 0, enter. So we have created one reference point and another reference point we have to create here, will be 18.528 comma 100 comma z direction we have depth 900 mm, so 900. Now click ok, then press escape. Then we have to create constraints, then mpc constraint continue, then create rp1, then unclick this create set and go to y-x direction and create and click on all these members which I have to tie by using shift and click, then done. Then control points leave not, click ok. So these have been tied. Similarly you have to tie this rp2. So take mpc constraint continue, so select mpc control point rp2, then select region for slave node, this three region by using shift and click, then done, then ok. So this node also have been tied. Then load, coming to loading, suppose I have given all this unit in newton and mm, so I apply a concentrated force, continue. So we have to select the point, suppose I have taken rp2, one end is hinge and one end is fixed, this is fixed and this is hinged. So rp2, I have selected rp2 and this will be x direction will be 0, y direction will be 0, and apply a unit force means 1, minus 1 means towards z direction, click on ok. So this arrow will show in z direction, we have applied the load. Then create boundary conditions, and then displacement rotation symmetry action, continue. Then we have to apply here at rp1, done. Encastre means this is fixed, encastre means fixed, so I have fixed this point, click ok. Then again create boundary condition for hinge support at rp2, that is at other end. Okay. Click on displacement rotation, click on rp2, click on done. Then u1 u2 you have to restrain in this direction, click on ok. Then movement at z direction, we have allow movement at z direction, x direction, y direction and force at z direction. Then click on machine, then you have to create, okay, this is the warning given. First you have to select a part, then global seeds. Assign global seed. The finer the global seed means the minimum the global size, the accurate will be your result. Suppose I take 10 global size, or you can take 5 or 2 mm, but that takes too much time. Then click OK. Then assign mesh controls. Then select region to be assigned. Then click on the region. Turn. Then quadrilateral meshing. OK. Then click mesh parts. Then OK to mesh part. So this is our meshing. So we have meshed this part. Then after meshing, go to job. Then in job, you have to create a job. Suppose I give a name, we use ABAQUS. Then continue. Then click OK. Then you have to submit it. Okay, this has been submitted, and we have to monitor it. Here we will see submitted. After this, running will come when the analysis starts. So the analysis is running. Here we will get warning, but we have to neglect this because we know the additional degree of freedom will be activated since we have given reference point and restraint to that direction. So it's okay. So this is running. This will take time. So, so we have got this completed. Dismiss. Then click on results. So for seeing deform shape, click on plot deform shape. So we have got deform shape, and eigenvalue is 51.054 Newton. Means 51.054 newtons means 51.054 kilonewton. So this much is the so another buckling, another type of buckling. So this is the local buckling. This occurs in half segment. Local buckling. All these are local buckling occurred in columns. We have got different values, but the lower will be the lower eigenvalue will be correct eigenvalue. So we can see contour plot also where the stresses are maximum, where the stresses are minimum. So here. And the answer for this is load carrying capacity of column is 51.054 kilonewton or 51054 newton. So in this way you can do analysis of any member. So thank you friends for watching this. Hit subscribe if you like this video, and hit like if you like this video.